Applications of Differential Calculus, page 5. Problem 7. A tank contains 50,000 liters of water. The tap is left fully on and all the water drains from the tank in 80 minutes. The volume of water remaining in the tank after t minutes is given by this function. Blank liters, where t is between 0 and 80, and that's minutes, right? Find dv dt and draw the graph dv dt against t. Okay, so let's see. dv dt is going to be equal to 50,000 times, and then we're going to do the power rule. And then we're going to do the chain rule. We're going to take the derivative of what's inside there. So it would be negative 1 over 80, because that's the coefficient for t. So let's multiply that out. So let's see. 80 cancels with 80 here. So it would be negative 1,000 times 2. So it would be negative 2,000. 1 minus t over 80. That's the dv dt. And then it says to draw a graph of that. This is actually a straight line. Let's do it on the calculator. So let's clear these out, and then we're going to type the function in, negative 2,000 times 1 minus t, which is, we'll put x because it's a calculator, divided by 80. And then we'll graph it, and we're going to have to adjust the height here. We'll do zoom fit, so to adjust the y. Wow, it's actually on the negative side. Okay, and so let's see. So yeah, it's like kind of a weird graph. It looks like this, and this intersection point is negative 2,000. And then let's see. This intersection point is it's about 80. Okay? Alright. So that was A. B, at what time was the outflow the fastest? Well, the volume of water is V, so, and the change in the water was V dashed. So the outflow is actually V dashed. So when was V dash the greatest? To find when V dash is the greatest, we would need the second derivative of the volume. So that would be, and let's simplify this. We're going to write it as negative 2,000 plus 2,000 divided by 80. Let's see what that is. 2,000 divided by 80. And then we'll delete that. Gives us 25. So it's negative 2,000 plus 25t. So the second derivative of that, or take another derivative of that, and we'll end up with 25. So let's skip B for a second and go directly to C. In an effort to find when the outflow was fastest, I looked for the second derivative of V, but then I found out that the second derivative of V is always plus 25. And then I look at C and it says, show that the second derivative of V is always constant and positive. There, we've just done that. Interpret this result. It means that the outflow is constantly reducing at a rate of 25 liters per minute squared. Okay? So, and it's plus 25, so it makes it look like it's increasing, but actually the outflow is a negative number. And so since the rate of change of the outflow is a positive number, that means that the outflow is getting steadily less fast. So actually, I was trying to find the maximum or minimum of the outflow, but actually remember that if there are no maximums and minimums, if there are no stationary points, then where are you going to look? You're going to look at the endpoints. So look at this graph of V dashed here. The endpoints would be here and here, and which one of those would represent when the outflow is fastest? Well, here the outflow is 0, so it's definitely not that. So it would be here, right? So the outflow is fastest at t equals 0. And this was the answer for C. Okay? So, and remember that the other parts of this graph, like this region here, we ignore because we're only looking at t between 0 and 80. Alright? Okay, let's move on to 9. A radioactive substance decays according to the formula W equals 20 e to the negative kt grams, where t is the time in hours. Find K given that after 50 hours the weight is 10 grams. Let's see. So the radioactive substance starts out at a certain amount, and then it gets smaller and smaller according to this function. Okay? And t is in hours. So let's find A. So it says find K given that 50 hours the weight is 10 grams. So first we write the function, and then they say to find the K such that after 50 hours the weight is 10 grams, so we're going to put 50, or we're going to put 10 in for the weight, and then the K is just going to be K, and then the T is going to be 50 hours. Okay, and then let's see, we're going to solve for the K there. We could use natural log. So let's first divide both sides by 20, so we get 0.5 equals e to the negative 50k. Then we take the natural log of both sides, so natural log of 0.5 and negative 50k. Natural log of 0.5 is, I feel like we've done this very recently. Natural log of 0.5 is negative 0.693 equals negative 50k. So we can get rid of both of these negative signs. And so now we have 0.693 divided by 50 equals k. So it's 0.693 divided by 50, which is 0.01386. Okay? So that was the answer for B. That was A. So B, find the weight of the radioactive substance at t equals 0, 24, and 1 week. And we can use the calculator to do this. We can put the function in here. So we're going to put 20 times e to the negative, and then we're going to put the k, negative k, which is 0.01386, t, which is x. And then we're going to look at the table. And then, so it asks, what is the value of the weight at t equals 0? And it will be 20. And at 24 hours, it would be 14.3. And at 1 week, it would be 24 times 7, which would be, let's see, (24 times 7 is 168. So now we just go down to 168. Takes a while, doesn't it? Okay, there's 168. 1.95 grams. Okay, it was 168 hours. Okay. How long will it take for the weight to reach 1 gram? It's getting close to 1 gram, as you can see here. One of the ways you can check to see how long it takes to get to 1 gram is you just keep going down and down and down until you see the Y get to, oh, there it went, 1 gram. So, 217, and it reaches 1 gram, 217 hours. Okay. And then find the rate of radioactive decay at T equals 100 hours and 1,000 hours. Now they're talking about the rate of radioactive decay. They're no longer talking about the weight. So the rate of radioactive decay would be the derivative of W. So let's take the derivative of that. So it's going to be 20 times negative K, which would be negative 0.01386, e to the negative 0.01386 t. Okay, and let's see. It says find the rate of decay at 100 or in 1,000 hours. So the rate of decay at 100 hours would be, and I'm going to multiply 0.0386 1386 times 20. So the negative 0.2772, and then I would put e to the negative, and then I'm going to multiply 0.01386 by 100, so it's going to give me 1.386. So that's 100. It's like W dash at 100. And then what about W dash at 1,000? That would be equal to negative 2772 e to the negative, and then we're actually going to move the decimal point one more point, so it would be 13.86. Just put 13.9. So let's see how much these would be. So e to the negative 1.386 times 0.2772. Okay, negative 0.0693. Okay, and so that is the rate of decay at 100 hours. The rate of decay at 1,000 hours would be e to the negative 13.9, and then I'm going to multiply that times negative 0.2772, and it'll be, wow, that's a super small number. It's negative 2.55 times 10 to the negative 7. Okay, so that is the answer for 1,000 hours. Then it says, show that dW dt is proportional to the weight of the substance remaining. Okay, so basically what they're saying is, show that W dash is equal to alpha times W. So W dash is negative 0.2772 e to the negative we'll just put k because it's so long, kt. And we're saying, hey, that's proportional to 20 e to the minus kt. So then we just put an alpha there. It's just a constant saying it's proportional. And so we can see that the negative e to the minus kt's cancel out, and what we end up with is that negative 0.2772 is equal to 20 alpha. So alpha is a constant, and yeah, that's fine. So yes, we have shown that the W dash is proportional to W. Okay. Last one, 11. The height of a certain species or shrub, T years after it's planted, is given by, and then there's this H function here. Got a log in it and everything. How high was the shrub when it was planted? So basically what they're asking for is, what was the height at time equals 0? So that would be 20 times the log of, and 3t would just be 0, the log of 2 plus 30. So let's calculate that out. First we'll do natural log of 2, 0.693. That looks familiar, doesn't it? Times 20. And then we add 30. 43.9 is the height in centimeters. Okay, how long will it take for the shrub to reach a height of 1 meter? So, we can use the calculator, or we can use natural log. And so let's use natural log. So we'll put b, and we'll say, hey, I'm going to say that the height is 1 meter. So I'm going to say 1 equals 20 natural log 3t plus 2 plus 30. Plus 30. And then I'm sorry, it says 1 meter. So 1 meter is actually 100 centimeters, right? So, and this function is in centimeters, so I'm going to put 100 there. Then I'm going to subtract 30 from both sides. And I'll get 70 equals 20 natural log 3t plus 2. And then I'm going to divide both sides by 20. So I have 7 divided by 2. These cancel out. So I have 7 divided by 2 is, or like 70 divided by 2 is the same thing as 7 divided by 2. It's 3.5, of course. Didn't need the calculator for that, did I? Okay, and then now that I have a natural log on one side and not on the other, I can take e to the both sides. So that would be e to the 3.5 equals 3t plus 2. And e to the 3.5 is 33.1, and then I'm going to subtract 2 from both sides. Get 31.11, and then I divide by 3 both sides, and I get that t equals 10.4. So at t equals 10.4, that is when the height reaches 100 centimeters. Okay. At what rate is the shrub's height changing 3 years after being planted and 10 years after being planted? So basically what they're asking for is h dash. So h dash is equal to, and let's take the derivative of this, we'll have 20, and then the derivative of natural log, remember, is 1 over the inside of the natural log. And then, of course, we need to do chain rule. And then the derivative of plus 30 is just 0. So we can simplify this. Now we have 60 divided by 3t plus 2. And what we're asking for is what was the change in height 3 years after being planted. So that would be 60 divided by 9 plus 2, which is equal to 60 divided by 11, which is equal to 5.45 centimeters per year squared, or not year squared, but year. Okay? And then 10 years after being planted would be h dash of 10, which is equal to 60 over 3 times 10 plus 2, which would be 32. 60 divided by 32 is 1.88 centimeters per year. Okay, so it's growing much slower 10 years after being planted. All right, and that's it for this page.